Hello everyone, this is my course Mastering ANSYS CFD from Zero to Expert, and this course was first published in 2018. And this course contains a lot of workshops and they are continuously being updated on the very regular basis. For example, recently I have added the one quiz, I have added the one role play. I will explain that thing, that's a for video is. And I have added the complete workshop, a new workshop, a laminar pipe flow with the theory and validation using the ANSYS workbench. And here we have gone through the first theory and the analytical approach and calculations for the our case scenario. Then there's a quiz that will like refresh your knowledge about whatever you learned in this lecture, and definitely from the presentation I am going to provide you, that is like also attached, and the ANSYS files also attached there. And then the first simulation, that is like a very quick and very simple to do. And then I have gave the lecture on the meshing and the mesh quality. And then I have proceed with the three different mesh types like multi-zone, sweep meshing, and the tetrahedron. And we have done the post-processing in CFD post. In first simulation, it was done in the Fluent. So you will learn both Fluent post-processing and CFD post-processing tools. Then I have gone to another like important topic, that is mesh dependence study. So here I have given the theoretical insights and how the mesh dependence is made. Then I have applied the same knowledge but on the practical scenarios, and we have done the mesh dependence in the workbench meshing, and then we have walk over through the advanced post processing in the Fluent and CFD post. And then also I have done the mesh independence with the ICM CFD hexa meshes, which I provided directly instead of creating them in the workbench. Then we have worked on the model reduction techniques like a half, full, quarter, and asymmetric approaches using the symmetry options. And also we have gone through the product modeling 30-degree sector with the tetrahedron and hexa meshing. And this also teaches you advanced commands and map meshing in the 30-degree sector with the advanced geometry decomposition and mesh control, and making the mesh product in the Fluent using the text interface. And then parametric study also is included in this project. And then the CFD project, that's the most important thing, where I have actually gone through the role playing, and that's the indication here. You will not see this role play in any CFD course. So what does it mean? And course fees is only $24.99, and this is valid for the coming 3 to 4 days. So now let me show you that how this is going to work. Okay, how this is going to work. So here is a role play, and I have used the one AA character that is there. There are some multiple characters are there. I use the one of the character, and I provided the name and the scenario and everything I did here. Okay. So here, if I preview the role, so see how this will proceed when you take this course and when you apply all the knowledge while doing all the exercises, all the lectures. So once you are done with every class, then at the end of that section you will see the role play here. Okay, so here I'm going to start the role play, and so this scenario is here. Okay, and the Dr. John is your supervisor or the project manager reviewing your report. Okay, so start the play.
Good morning. I've reviewed your initial CFD simulations for laminar pipe flow at Reynolds numbers 100, 200, and 300. Before we dive deeper, could you walk me through your setup choices, geometry, meshing, and boundary conditions, and explain how well your results compare with the analytical solutions?
The geometry I made is diameter of 1 meter, and the length is equal to 40 meters. Why? Because the entrance region length was, from the formula, it is like a 5 to 10 meters. So the remaining portion is when the flow is fully developed. And the boundary conditions are velocity inlet and pressure outlet. On the wall with a no slip condition. And our results were compared very well with the analytical solution.
All right, you've kept the pipe length sufficiently long to allow the flow to transition to a fully developed profile beyond the entrance region. Great call. The no-slip condition at the walls is spot on for this setup. I'm curious, though, about your mesh design. How did you tackle the meshing to ensure good resolution in this long geometry, especially around the wall regions?
Here I have used the different meshing methods, tetrahedron, sweeping meshing method, and the multi-zone. But I prefer the sweep meshing because I can control the meshing in the boundary layer. I can through the different options in the ANSYS meshing, the mesh resolution like a ratio in the along the normal to the wall, and also I control the mesh along the length as well. So and also along the periphery of the circular cylinder. So it ensures that we have the enough mesh resolution in our simulation.
That's a solid choice. Sweep meshing really gives superb control, especially for achieving fine resolution near the wall, which is critical for accurately capturing the velocity gradients in laminar flow. With those refinements near the wall and along the pipe length, your setup must be resolving the boundary layer quite well. Did you also perform any mesh independent study to confirm that your results aren't influenced by mesh density?
Yes, I did. I have made 3 meshes, 21,000 cells, 41,000 cells, and 80,000 cells. And on the last 2 meshes, 41,000, 80,000 mesh cells, they are giving me the similar results, same results with less than 1% error. So I choose the second mesh, that is I called as a medium mesh.
Great. It sounds like you've done a careful mesh independence study. Settling on the medium mesh with 41,000 cells makes a lot of sense. It balances computational efficiency and accuracy. That less than 1% difference between medium and fine meshes really shows your results are stable. Now, how do the key metrics like velocity profiles or pressure drop compare with the analytical solution? Any specific areas where you noticed minor deviations?
Yes, I have compared the velocity profiles at the 35 meters length because that is the region when the flow is fully developed. Pressure drop is also like a linear as in the CFD and the analytical approach. Both are comparing very well. But I did notice the deviation in the analytical approach and CFD approach when I analyze them in the developing region. In the developing region, that is the entrance region of the pipe.
That's an insightful observation. It's expected to see deviations in the developing region since the flow hasn't yet achieved the stability of a fully developed profile there. And numerical solvers can behave differently in capturing these transitions. What's crucial is that your results match closely in the fully developed section, confirming the accuracy of your setup. Did you quantify how significant these deviations were in the entrance region, or were they more qualitative observations?
Actually, I have plotted the pressure profile using the analytical expression and then from the CFD on the center line. So I can see the deviation there in the graph in the entrance region. The error might be 5 to 10% in the entrance region, but then the zero in the or less, like around 0 or like less than 1% in the remaining region.
That's a thorough analysis. A 5 to 10% error in the entrance region is understandable given the transient effects and high gradients that numerical models might struggle with. The almost negligible error in the fully developed zone really validates your setup. It's clear your model is doing a great job. Where it really matters for steady state results. Out of curiosity, are there any particular strategies or adjustments you're considering for mitigating the entrance region discrepancies in future studies?
No, actually the analytical solution does not give you the any solution or equations for the entrance region. So comparing them is like meaningless. We cannot compare them through CFD. CFD is giving everything. Analytical solution is only for the developing region. So we cannot compare them. So I'm not going to do it.
Absolutely, you're correct. The analytical solutions are solely derived under the assumption of fully developed flow. So it's not fair to directly compare entrance region behaviors to the CFD predictions. Your reasoning makes perfect sense. It's fantastic that you've clearly distinguished this. Focusing on the fully developed regime is indeed the right approach for validation here. Great work overall. Is there anything else you'd like to discuss in terms of results or next steps?
I would like to validate my CFD at the higher nonce number, that is like close to the range of 2300, where the flow is going to be transitioning from the laminar to turbulent flow. So I will be going for the laminar flow at 2000 nonce number, but I am like afraid that my entrance region length will be very very large, and that will be like a lot of load on my computational resources.
That's an ambitious yet exciting direction. At Reynolds numbers approaching 2300, you're right. The entrance length becomes significantly larger, and capturing the transitional behavior is computationally intense. One way you could handle this is by leveraging periodic boundary conditions or refining the mesh selectively in regions of interest. Have you also considered hybrid approaches or simpler assumptions that could limit the computational burden while still providing reliable insights?
Actually, I did it. So I can like handle this one by modeling the only fully developed region, and I can like escape the or remove the my entrance region by providing the velocity profile through GDF or the expressions. So that will address that challenge.
That's a great workaround. By supplying a fully developed velocity profile at the inlet, you're effectively bypassing the need to model the entrance region while saving on computational resources. It also narrows the focus of the study to the important segment of the flow. This approach is efficient and highly practical. Sounds like you've got it all figured out. Well done. Anything else you'd like to share or discuss?
No, do you have any feedback or comments? Thank you.
You've done an excellent job setting up and validating your CFD simulations. Your approach is practical and thoughtfully reasoned, especially how you've handled the entrance region and meshing. Keep up this attention to detail. If you keep using strategies like this, you'll tackle even more complex simulations effectively. Great work overall, and thank you for sharing.